Welcome back, everyone. So we have the great pleasure today to welcome Professor Natasha Movchan from the University of Liverpool. She is a world expert in elasticity theory and metamaterials and asymptotic methods. And Natasha today is going to talk on elastic chirality in metamaterials. Professor Movchan.
Hello, everyone. I hope you can hear me well. If you can't, just let me know. I'm going to share screen here, by the way, Sebastian and everyone else. Invitation. Just some time. Select the screen. Sorry. So I'm going to share my screen. And you should now see my first slide. Can you see it?
Yes, we can.
Yeah, okay, brilliant. So I'm going to talk about waves in elastic chiral lattice systems. And this talk, as you can see from the what I've written on my slide, is based on the recent work we did together with Carta, Ian Jones, and Natasha Movchan. So what I'm going to talk today about is I will begin by looking at a simple dynamic elastic lattice, and it will be a triangular lattice. And I will revisit the characterization of waves using the notion of lattice flux and lattice circulation. And then I will talk about chiral elastic lattice. It will also be triangular lattice, but it will be chiral. So there will be some additional elements added which make it chiral. And what I will be most interested is its additional waveforms, which are called here Vortex waveforms. I will also talk about wave polarization and dynamic degeneracy and how actually use the notion of lattice flux and lattice circulation to characterize waves in chiral elastic lattice. And finally, I will talk about dynamic coupling, where I will look at a very simple example of a chiral elastic chain, which will be a one-dimensional object geometrically, but it will still support two-dimensional waves. This talk will be based on the three papers which I mentioned here, which we recently published in 2019 and 2020 on these three topics. So to begin with, let us start with triangular lattice, which part of which is shown here. So we have just a simple infinite periodic triangular array of point masses, which are connected by these elastic links. We assume that the stiffness of these links is C, and they have specific lengths, which we will call here L. We will assume that these masses are constrained to move in the plane, which we will call x1, x2 plane, and their displacements will be assumed to be small, as to be able to use linear elasticity setting. We will be looking at a time harmonic regime, so we will assume that there is a sort of specific dependence on time by this factor, where omega is the radiant frequency, and we will use the fact that we have a periodic structure, and we will look at so-called Bloch-Floquet waves, where we will employ the quasi-periodicity condition, which is written down here, which allows us to rephrase everything which happens in the neighboring cell to what happens in chosen the central cell, as it says here. Now, when we start writing the governing equations, which are effectively the equations of motion, we can write them in a very compact form, where U represents the displacement vector, and we have several quantities here, one of which is the stiffness matrix, matrix C, and we also have the mass matrix, capital M. In this particular setting, when we have just a normal monatomic lattice, which is where the point mass is connected by massless elastic links, both matrices are sort of look like this, and the mass matrix is the diagonal matrix. And the usual way to deal with it is to look at the solvability condition for this system, which then leads to a dispersion relation, which is written down here. And this dispersion relation, which is in fact a quadratic equation for square of the radiant frequency. Now, please note that here our frequency was just normalized by this quantity root of C over M. Now, if we look at this particular dispersion relation, we can solve this equation and write down the roots of this equation. Here we only have two positive roots due to the meaning of the frequency. We can, for the surfaces in this particular case, which are dispersion surfaces, which represent two solutions in the K1, K2 plane. We can see that we have the lower surface and the upper surface, and there's a cutoff frequency above which there are no dispersion surfaces. That means that for frequency above this cutoff frequency, there are no waves propagated through the system. Now, here is the expression for the stiffness matrix, which is written down here. This stiffness matrix depends on K1 and K2 as well. Now, this is we can see that unfortunately on this picture you can't see what happens near the origin. But what happens near the origin is similar to what happens in the vicinity of this point, for example, with the only difference that we have a complete two cones starting at the origin. We can see that these are, for small values of K, that will be sort of circular cones, which implies that the dynamic response of this lattice in the low frequency regime is isotropic. There are no differential directions as such. All the directions are in a way equivalent. But this only happens in the low frequency regime. As we go, the low frequency regime for small values of K as well. If we go for larger values of K, we can see that the surfaces become very complicated, and that leads to the notion of the dynamic anisotropy. So our lattice, although it looks very simple, it will exhibit some kind of dynamic, different dynamic response for different frequencies. Now, if we want to find the eigenvectors corresponding to the given eigenvalues, what we find is that, by the way, the system we need to solve to find the components of these eigenvectors. We find that these eigenvectors are real and they are orthogonal. So the two eigenvectors on two different surfaces are orthogonal. Now, what this means that if we try to write down the expression for the time harmonic displacement of a lattice particle for the given eigenmode, it will have this particular, apologies, I have some people riding motorbikes around. So the displacement of particle will have this particular very easy to interpret form. And what it leads to the fact that the trajectory of each lattice particle is in fact a straight line. And this happens for just normal monotonic triangular lattice. Now, what we want to talk about now is we have case when we have k tending to 0, so if we consider the long wave limit, we can, in the long wave limit, our lattice approximates a continuum. And in this case, we can distinguish in a continuum setting, we can distinguish between two different types of waves, one of which is a pressure wave and the other one is the shear wave. And the way we distinguish between these two waves in a continuum is we look at whether the displacement vector is parallel or perpendicular to the wave vector k. So if it is perpendicular to the vector k, we have shear wave, and if it is parallel to the vector k, it will be a pressure wave. But this is for respond to a continuum. The question is, can we use the same type of description for a lattice? And it seems that in the low frequency regime, or the long wave length limit, we probably can, because we say that the lattice approximates a continuum. What we said to do was, we wanted to find whether there is any quantity which could be used in a case when modulus of k is not small. And we came up with the notion of the lattice flux and lattice circulation, which are similar to the notion of flux and circulation in the continuum, but applied to a lattice. And we wrote down the representations for these two quantities, which involve the vector f. This vector f, the vector which will be actually, which we are going to use to characterize the waves in a triangular lattice, analogous to the vector k, wave vector k, which is used in a continuum. Interestingly enough, in the long wave limit, these two vectors are parallel to each other, and therefore we can think of shear type waves corresponding to a continuum as being flux-free waves, because when u is perpendicular to k and therefore u is perpendicular to f, we have zero flux, and we have shear type waves in the continuum. And similarly, we can look at the so-called circulation-free waves, where u is parallel to the vector f, which we introduce here. And in the long wave limit, because f is parallel to k, this will correspond to a pressure wave in the continuum definition. So with this in mind, because there is some correspondence, nice correspondence between these two vectors and these two types of descriptions of waves in a continuum and in a lattice in the long wave limit, we are going to use this quantity, this vector f, which is defined here, and say that in the lattice we will distinguish between two different types of waves. Circulation-free waves, where vector u is parallel to the vector f, and in this case the circulation vanishes. And then we will look at so-called flux-free waves, where the vector u is perpendicular to f, and therefore the flux is equal to 0. And as I said before, in the long wave limit, these two descriptions are very similar to each other. Now, so if, let me go back to the slide again. So with this in mind, we are going to use this vector f and the notion of lattice flux and lattice circulation to describe the type of waves we have in a lattice for all values of vector k, small and non-small. Now, since the trajectory of the lattice particles are straight lines, we can sort of imagine how the particles move within the lattice. And generally, these trajectories are neither parallel nor perpendicular to the vector f. And over here, I have on the right-hand side of my slide, I have a diagram which shows the trajectories. The dashed line corresponds the trajectory of a particle corresponding to the frequency taken from the low dispersion surface, and the dot dashed line corresponds to the frequency taken from the upper dispersion surface for a specific choice of the vector k, which is not small. In this case, the two vectors, vector f, which is associated with the notion of lattice flux and lattice circulation, and the vector k are not the same, and they have even different directions. And we can find the angles between the vector f and the corresponding trajectories for the lower and the upper surfaces, which are called here beta 1 and beta 2. And these two vectors are neither 0 nor pi over 2 in the general case. The thing which is important here is that the two trajectories are perpendicular to each other, because the corresponding eigenvectors we set for the frequencies on the lower surface and for the corresponding frequency on the upper surface are orthogonal to each other. And we can see in the picture that they are orthogonal to each other. Now, the interesting thing which comes from exploiting the notion of lattice flux and lattice circulation is that if we start looking at the description of waves in the K1, K2 plane, and look at some specific lines, which are described here, 12 of those, in these lines, we will have specific orientation of the displacement vector and the vector f. In particular, on these lines, on the low dispersion surface, U will be orthogonal to F. So on these lines, we will have so-called pure flux-free waves. And on the upper dispersion surface, when we choose the frequency from the upper dispersion surface, we will have U being parallel to this vector F, which will correspond to the case where the corresponding waves in the lattice are so-called pure circulation free waves. And this happens when k is not small, which is important. So for small k, we can definitely say that on the low dispersion surface we have flux free waves, and on the upper dispersion surface we have circulation free waves. But there are some additional lines for non-small values of k, where again we have a so-called clear-cut flux-free or circulation-free waves, depending on the frequency. There are also some points where, which are marked here by crosses on the diagram, where both flux and circulation are equal to 0. And this happens because the vector f vanishes at those points. And we come back to those points when we start looking at the chiral lattice associated with the triangular lattice. And we will see why the points are important a bit later in the talk. So with all of that, I'm now going to see how this notion of lattice flux and lattice circulation and applied to the case of so-called two-dimensional chiral elastic lattice. So what we are going to do here is we are going to take again the triangular lattice as the one we had before, but now we put it on we are putting it on the level of gyroscopic spinors. So what we have the same type of monoclinic lattice as before. All masses are the same. The lattice is periodic and triangular, but we now have connected each mass to a gyroscopic spinor, which in equilibrium position stands vertically, as shown here, and it rotates with some sort of speed. Now, what we will assume is that, again, we will assume that the motion of the particles within the lattice is restricted to the x1, x2 plane. And that will imply that the angle theta, the angle of nutation, should actually be small for it to be straight and being small and being all the displacements being in the same plane. We will assume that the axis of each gyroscope, which is pinned at the bottom, as you can see, and is free to rotate at the lattice junction, is perpendicular to the x1, x2 plane in the antipolar configuration. Now, when the lattice moves, the tip of the connected gyro will undergo the same displacement as the displacement of the corresponding mass, the node. And the spinner will start precessing. And then because it's precessing, it will generate a force in the plane of the lattice, which is perpendicular to the displacement of the lattice particle. We are going to neglect all the forces perpendicular to the plane of the lattice, such as gravity, and assume, as I mentioned earlier, that the displacement of the lattice is confined to the x1, x2 plane. So we will introduce some quantity, which we will call a spinor constant, and which is denoted here by alpha. It could be evaluated in a specific setting, and it has been done by Brun, Johnson, Movchan in 2012. I'm just going to use the notion of this constant without specifying what this is. So, sorry, that is a bit slide. So we are looking at the bottom left corner, where we have formal setting of the problem. So, if we write down the equation of motion in chiral lattice, assuming that we have time harmonic motion, we can see that the equation is very similar to the one we have for a normal triangular lattice, with one difference. We have the matrix, which is called here matrix A, and this is a spinor matrix. By the look of it, it has non-zero off-diagonal terms, and what these off-diagonal terms do, they couple the displacements in the x1 and x2 direction, and this is the role of the spinor matrix. The mass matrix is still diagonal as before, and the stiffness matrix is still the same as before. And we again use the same type of quasi-periodicity condition as we used for normal triangular lattice. But the only difference due to having gyros is this additional inertial term described by the spinor matrix A. This term, of course, when we start looking at the dispersion relation, which is written down at the top right whole corner, we will have the contribution of the spinor constant alpha in this term. And we can draw the dispersion surfaces for some normalized frequencies. And here I have the comparison between the two sets of dispersion surfaces. For the non-chiral case, when alpha is equal to 0, the two surfaces I have shown previously, now they are in blue and red. And on the right-hand side, part B corresponds to the case when we have some kind of spinors, with the normalized spin constant half. If you look at this two sets of dispersion surfaces, we can see that they are different. So the top surface goes up, and we lose the points where the previously, for the case of just normal triangular lattice, there was the two surfaces touched at this point, but now they no longer touch, except for the origin and these edges. And the interesting thing associated with this dispersion relation, which accounts for the effect of gyroscopes, is that this dispersion equation degenerates when this parameter alpha, normalized parameter alpha, is equal to 1. Because this first term disappears. A consequence of that is that one of the dispersion curves is no longer there. Let us have a look at the next slide. So here I have the dispersion relation repeated, and the expressions for the two roots of the dispersion relation for alpha, which is smaller than 1. And as I said before, when alpha is equal to 1, our equation degenerates and we have only one dispersion surface. And the effect of this degeneracy was discussed in these two papers, which I mentioned here. And I'm not going to look at the effects of degeneracy. What I'm interested in is applying the lattice flux and lattice circulation strategy to describe the waves in this chiral lattice. So going to again look at the eigenvectors and associated with these eigenvalues on the two surfaces. But because we now have the effect of gyroscopes, our eigenvectors are generally non-orthogonal. In fact, they satisfy this particular relation, which obviously when we ignore the when alpha is equal to 0, the matrix R, which is written down here, vanishes, and we end up with the orthogonality condition we have in non-chiral case when alpha is equal to 0. But in the chiral case, this term is present, and that means that our eigenvectors are non-orthogonal. One can say, well, okay, fine, they are non-orthogonal. Well, what's more, they are actually complex. And what does it mean in terms of the trajectories? Trajectories of the particles are ellipses, in fact, because the eigenvectors are complex. And as we heard and as we know from previous discussion, in the case when we have parameter alpha is equal to 0, so in the non-chiral case, our particle trajectories are straight lines. So is there any relationship between the trajectories we have in the non-chiral case and in the case we have when we have non-zero parameter alpha in the chiral case? Let us see. So what we are going to do to characterize waves in the chiral lattice is that we are going to, here we have an ellipse, which is not necessarily aligned with the x1, x2 axis. It has its own local system, x1, x2. On this diagram, we also have the direction of the vector f, and u is our displacement vector. So this is the general case where the two vectors are not parallel, nor orthogonal to each other. What we are going to do in this case, we are going to split this vector u into two parts, one of which is the so-called straight line component, which is parallel to the major axis of the ellipse. And it corresponds to a straight line motion parallel to this axis. And also, we will introduce the second part of this vector, uv, which is shown here in blue. And we will call it Vortex component because it corresponds to circular motion. So this vector u traverses a circle, specific radius A, which is the radius of the minor axis, and U is always parallel. UL is always parallel to the major axis of the ellipse. The interesting thing about the orientation of this major axis relative to the vector F is identical to the angle between the same vector F and the straight trajectory of the particle in the non-chiral case. So the orientation of the major axis of the ellipse, which describes the motion, which represents the trajectory of the lattice particle, is the same as the direction of the motion when we have non-chiral case, which is nice. And when we start increasing the parameter alpha, the resulting ellipses become more narrow, and their major axis, the orientation of the major axis remains fixed when we take when we change alpha, and in the limit we retrieve the straight line motion in the direction of the major axis, which we observe in the corresponding non-chiral case. That is some kind of, I wouldn't say justification, but it's a nice thing about this type of split of the decomposition of the vector U in this case. So in the non-chiral case, as I said previously, U will be equal to 0 because there will be no vortex component, and U will coincide with UL. We can also further decompose the straight line component into the component which is parallel to F and thus characterized by zero circulation, and which is perpendicular to F and thus has zero flux. Now, over here on these two figures, I have the generic trajectory. The trajectory of generic particle. In the case when the spinor constant is taken half, just some value between 0 and 1. And on the left-hand side, we have the trajectory for the low dispersion surface, and on the right-hand side, for the upper dispersion surface. And you can see that they are calculated for the vector k, which is not small. Over here, we have also shown the components, the dot circles correspond to the vortex component of the displacement. And what we notice is that, as we discussed for the case of non-chiral lattice, the directions of motion on the lower surface and the upper surface were perpendicular to each other. And we can see that these two ellipses have their major axis perpendicular to each other as well. But this is not the only difference. We can, over here, we have some plots of trajectories, and we can see that these trajectories generally have different sort of shape. They are all elliptical. Sometimes they may be aligned with the lattice links, or may not necessarily be aligned, be at an angle. And in the two sets of diagrams on the left, these two correspond to the case when the two vectors, k and f, are parallel to each other. Now, the first two diagrams, parts A and B, correspond to the case when the vector k is small. And in this case, both k and f are parallel. And the two diagrams correspond to the lower surface on the left and the upper surface on the right. The parts C and D correspond to, again, to the case when k and f are parallel, but here vector k is no longer small. And we can see that we also have elliptic trajectories. They are somewhat different compared to the case of a small value of k. Now, in parts E and F, we have just a general point k in the k1, k2 plane, and here vectors k and f are non-parallel to each other. And finally, the diagrams which are highlighted here in the blue box correspond to the case when the vector f is 0, which means this is the case when we have circulation and flux are both equal to 0. If we go back to the description of the displacement, that would imply that our linear component, straight line component, is actually equal to 0. And the only type of motion is associated with the vortex component. And we can see that the trajectories in this case are circular. I'm going to show you some movies. I'm going to make these two movies move. And this corresponds to the case when not only are the linear components for the value of k, which is small. And we can see that at the top, this diagram corresponds to the case when we look at the low surface. In this case, the motion is perpendicular to the vector f. The vector f is shown in green and k is in magenta. And at the bottom surface, we have the motion in the direction of the vector f. So this one corresponds to so-called parallel, which means free, and then perpendicular we have flux free. I'm going to show the vortex components now. And what I want to notice is that not only the size of the circle, but also the direction. If you look at the direction in which particles move on the low surface at the top of this diagram, have it rotating counterclockwise, and at the bottom, at the bottom diagram, we have the upper dispersion surface where they rotate in the direction. And I'm now going to click on the total displacement, and you can see the resulting elliptical trajectory, which is a straight combination of the linear component and the vortex component. Just get to the next one. Over here we have again the movies corresponding to the case when both f and k are parallel, but this time around k is no longer small. So I'm going to make the move. And you can see that the trajectories are more complicated. Again, the linear components are either parallel or perpendicular to the vector f. And then we have circular motion where the rotation is different for different, the direction of rotation is different for different surfaces. So let me now look at the case when the two vectors f and k are not parallel to each other. I'm going to set all of them in motion again. You can see that in terms of the vortex component, we will have the same type of difference in the direction of rotation. On the low surface, we will have rotation in the counterclockwise direction, and on the upper surface, it will rotate in the clockwise direction. So, finally, I would like to show you some movies corresponding to the case and f is equal to 0. So we have so-called Vortex waveforms. Again, I'm going to set all of them moving. And you can see that although I clicked on the two movies in the left column corresponding to the linear component, there is no motion because it's equal to 0. And we have only vortex component which contributes the total displacement. And this is the example of the pure vortex waveforms in this case. So we can also evaluate, too far. We can also evaluate the lattice flux and lattice circulation for the vortex components. They will differ per phase and will have the same amplitude. And for the straight line components, the tangential component will have zero circulation and no zero flux, which is, of course, amplitude is given in here. And for the normal component, the flux will be zero and the circulation is non-zero. Now, we can also plot this lattice flux and lattice circulation. In fact, we plot here the amplitudes of those defined as the maximum of the module length. And what we are interested in finding the points on the amplitude plane where we have vortex waves. For this, we need to look at these ratios of the lattice flux and lattice circulation amplitude and find the points where these ratios on each surface tend to 1. And it happens that, in particular, in the limit case of the generacy when alpha tends to 1, we have this vortex waveforms, which occur much everywhere in most of the places. No, I'm doing this time. So what we found so far is that when we look at the chiral elastic lattice, we can introduce the notion of lattice flux and lattice circulation to define or characterize the waves. There will be a straight line component, which is similar to the one we have in the direction to the one we have in non-chiral lattice. But chirality brings an additional waveforms, the so-called vortex waveforms. The last part of my talk is related to coupling of waves in chiral discrete elastic chains. So we wanted to look closely at how the waves of different components of the wave vector couple. And this was a simple example. So imagine we have a discrete chain, just a single chain of forces connected by some links. And we add some gyroscopic spinors. We have not only the stiffness matrix, but also have some contribution to the term which is responsible for inertia. So we have additional, our infinite chain contains inertial elements. So we have, imagine we have all the nodes attached to each other and then standing on gyroscopes in similar fashion as we had for the case of a lattice. And we assume that our infinite chain possesses translational and gyroscopic rotational inertia. And we also allow for some pretension in the chain in the longitudinal and transverse direction. So the system of equations we have here says that although our chain is geometrically one-dimensional, the elastic waves which we will have in such a chain will have both longitudinal and transverse components. Hence, we have this vector U, and which has two components. We again use the quasi-periodicity condition and write down and look at the time harmonic waves, of course, and write down the list of equations in this particular form. And we noticed that chirality induces coupling between two components of the, that should be U2, sorry, there is a printer here, between two components of the displacement. So we can use some normalization and write down the system in the system form rather than matrix form. You can see these two terms which effectively are responsible for coupling in that particular system. This system of equations, although it may be linked to, for example, an electromagnetic wave in a periodically magnetized medium, here we link it to a mechanical wave in an elastic retention to infinite string with periodically distributed masses attached to gyroscopic spins, and solve a dispersion relation in a similar fashion as one would do for when studying Bloch-Floquet waves. And here, this quantity sigma, which we have in the dispersion relation, has a particular form. So it's again polynomial, quadratic polynomial for omega squared, and we have contribution of the heuristic constant alpha here, as well as pretension constant C. Now, when we evaluate the roots of this equation, we can write omega squared plus or minus in this particular form, where this quantity omega squared is in fact given here, and it corresponds to the frequency of waves in a classical 1D monatomic infinite chain. And this polynomial, this quantities p plus minus, which depend on alpha, which are heuristic parameter, and this constant, which is responsible for pretension, have this particular form. And over here, I have a graph which shows omega plus and minus as functions of k alpha for a given, for the chosen value of C. So if we look at the eigenvectors, because we have some effect of chirality, we expect them to have some pretty complex. And in fact, we can write them in this particular form where the first component is purely imaginary because quantities p plus minus are both real for the choice of parameters alpha and c. And the resulting elliptic trajectories, which are written down here in the local system of coordinates associated with elliptical trajectory for each node, these are ellipses aligned parallel or perpendicular to the chain. And in fact, for the plus node, the ellipses will be aligned with its major axis along the chain, and for the minus mode, it will be the other way around, perpendicular to the chain. What I would like to talk about now is the dynamic Green's matrix. So let us imagine that what we do now is look at our, we now add a force applied at the central node. It has the same frequency as the frequency of operation of the chain. And what we do, if we want to solve this system, we can use the discrete Fourier transform and write down the representation for the solution via the Green's matrix, whose Fourier transform has the particular form. Now, to find the Green's matrix, we need to find these quantities, which are called here Fn. And these quantities depend on the node, on the parameter omega, which is capital omega, which is omega squared, alpha, and c. It will depend on whether the forcing frequency within the stop band, pass band, or partial pass band. I go back to this picture, we can see that if you just concentrate on a chosen value of alpha, we have two different dispersion curves, and below this frequency, when we have both curves, we have total passband. In between these 2 points, the point where the first dispersion curve finishes and the cutoff frequency, we have the so-called partial passband. Above it, above the cutoff frequency, we have the stop band. So when we evaluate, I'm going back to the slide on dynamic Green's matrix, when we evaluate these quantities F, which are included in the representation for the dynamic Green's matrix, the way we evaluate it will depend on whether our photon frequency within the stop band, pass band, or partial pass band. And in fact, this quantity capital F, which we have here, can be written in this particular form, where lambda plus minus is associated with this polynomials p plus minus we have in the representation for the ideal frequencies. Now, we can rephrase this in terms of the bands for passband, partial passband, and stop band in terms of the quantity capital omega, which is in fact little omega squared. And it will be a function of these quantities A plus and minus, and will be given by whether they are bigger or smaller than 1. To split it up. Here on this slide, we have the representations for these quantities F, which are present in the Green's matrix. And we can see that if we construct it for the stop band, both terms we have here, they correspond to, they are exponentially localized. For partial passband, we expect to have one term which is propagating and the other one which is evanescent, which is exactly the case. And in the total passband, both terms are propagating, as we would expect. Now, here is the illustrative computation, which includes all 3 regimes, where we apply force components 1 and 8, as stated here, for different frequencies within the stop band, the top diagram, part B, the partial passband, the diagram of part C, and the total passband, which is part D. And this is all associated with where the frequency is. So in the total passband, we are somewhere here below this frequency where the red curve finishes. In the passband, partial passband, we are between these 2 frequencies, and in the stop band, we are above all these dispersion curves. So, if, for example, we look at the trajectories for frequency within the stop band, look at the force problem where the force is applied at this node, the 0 node, and we have some retention. C is equal to 0.8. And we can see that the biggest ellipses at the point where we apply, at the node where we apply the force, and we can see that the radius of trajectories, the size of the trajectories, diminishes quite quickly when we go away from the point where we apply the force, because of the platform is in the stop band. In the partial passband, we have some different distribution of trajectory. Again, by the force somewhere here at the 0. And we can see we have one of the waves propagating, but the other one is still propagating. Therefore, we can see that the size of the trajectories, the displacements are not decaying very rapidly as in the of the band. And in the passband, of course, we can't really distinguish which one is the point where we are applying the force. It's again in the 0 position. And we can see that this corresponds to a case of retention, and both ways provide corresponding to both dispersion curves. Do I have a time, or shall I stop now, Sebastian? I have some additional couple of slides about dynamic degeneracy. We remove.
Please go ahead.
Okay.
Lots of time, as long as you want.
Okay. So, just 2 moments. These are just the slides corresponding to the case. What happens if we remove the retention? So we say that there is no transverse tension anymore. We set this parameter C to 0. And in this case, we will have only 2 regimes. We will have only one dispersion curve, and we have 2 regimes, either passband or the stop band. The Green's matrix in this case simplifies dramatically, and it has, in the stop band, it has quite structure, so it's exponentially localized, and in the passband, this is a propagating type of expressions. I'm going to go straight to the movies for this particular case when we have, which I referred to for the 2 cases when we have the stop band frequency. We can see that we have, for the first problem when we have transfer potential, we still have a similar picture, but here all the other nodes, except for the one which we apply code, they have elliptic trajectories with major axis oriented along the chain. This is the only one which isn't, because our host is at an angle. If we look at the case of a passband, when we choose the frequency from the passband, similar picture is present. Again, except for the 0 node, we apply the all the other nodes have elliptic trajectories where the major axis is aligned with the chain. And that's okay when we still have telescopes, but we remove transportation. So I probably should stop now. Thank you very much for attention.
Thank you so much, Professor Movchan. So I've got the voice of this guy in Star Wars. Okay. Any questions from the audience? I've got many, please.